Today in physics, we're going to be talking about machines. And the machines, sometimes we think of really complicated machines, but machines don't have to be complicated. Machines can be really any kind of device that can make work easier. And we define work, remember, as the what? The force times the distance. Good. So work is force times distance. So what it's going to do is it's either going to multiply the force, because if you're able to put in a little force, it can take that and magnify it so that the output is a lot of force. Like, for example, if you need to use a jack in your car when you have a flat tire or some kind of something that you need to do. Personally, most of us can't just lift up a car, okay? So you'd have to use some kind of device. So the machine that you would use to do that would take your little bit of force and magnify it into a large amount of force. Or it can take and magnify the distance. So you put in a lot of force and don't really necessarily accomplish getting a huge force out. Maybe your force is diminished, but it changes the direction of force, or it changes the distance that's achieved. So it can help you out to do work in that way. For example, if you've ever been fishing, anybody been fishing? Mm-hmm. Yep. So you've been fishing and you're pulling on that fishing pole and it feels like the fish is really heavy, and you pick it up and it's maybe like if you're really, really blessed, it's a 1 pound fish. Okay, but you're like putting in all this effort and it feels like you're fighting against a whale or something. And that's because the purpose of a fishing rod, even though that is considered a machine, is not to multiply the force, because you can put in a lot of force right where you're pulling at it, but it's going to change and multiply the distance. Okay, and Marcus isn't going to get to see this part, but since I've got this pole here, if you pull up, what you notice is you're pulling and the distance on the end of that is much further than the distance you pull. So the purpose of something like that is not to multiply the force, but it's to multiply the distance in that. Okay, so a machine is a device that's used to help make your work easier. And it can multiply force, multiply distance, or change the direction of force. So I've talked a little bit about multiplying the force, like with a car jack, or multiplying the distance, like with the fishing pole. Also, a baseball bat would be the same type of deal where it multiplies the distance, because the little end of the bat, yeah, exactly. It's a certain type of lever. And you've got the bat and you're swinging it around. So you've got, like the big arc of the swing, it multiplies distance, but you're swinging super hard to put a little force into that ball, and then it affects the ball in a big way. Or the other purpose is to change the direction of a force. For example, in a pulley system, you pull in one direction and it could go through that whole system, weave all around, and it changes the direction. So it may not necessarily be that it multiplies the force, but in the changing of the direction of the force, that can be just what's needed. So you can pull in a certain amount. If I had a pulley that went up over like the top of a branch of a tree or something, I could actually lift something that's my body weight if all I did was like wrap the rope around my waist and fall on the ground. Then I could lift something on the other side that's my body weight. But if you ask me to just lift something that's my body weight, I can't do it. But so changing the direction of force sometimes is what's needed to help make the work easier, changing the force and the distance. Okay. Now the effort force, okay, when you make an effort, you think of, okay, I'm doing something. The effort force is that force that you put into the machine. So effort goes in to making this thing happen. And So every one of the machines that we're going to talk about and the machines that we're going to look at involve, there's some place that you have to put force into the thing. And the force out would be really convenient if it had something like output force or something like that, but we call it the resistance force, okay? Because you're going against some kind of a resistance, and it kind of is a little hard to get your mind around that, but if that word resistance doesn't really come into mind, think of it as the result, and then that will remind you that that's the force that's coming out of the machine. So the effort goes in. I push the little handle on my car jack, or I turn the crank on my car jack, and then the result is that the car lifts up. That's the resistance force, is the amount of force that is applied to my car then. So you've always got an input force and you've got an output force, an effort and a resistance. And it is often useful for us to have forces that will increase because it's just extremely helpful. And it gives you an advantage. We call that advantage that we have in the physical world a mechanical advantage. So our mechanical advantage is a ratio of the result resistance force divided by the effort that you put in. So if your numerator, if your result or your resistance is greater than the effort that you put in, the fraction comes out, so the mechanical advantage is greater than 1. And so in many cases, we want the mechanical advantage to be greater than 1, and that word advantage is like that. If the mechanical advantage equals 1, that means we didn't multiply force at all. Maybe our machine was doing something like changing direction. And if our mechanical advantage is less than 1, that means we didn't multiply force at all. As a matter of fact, the force out is less than the force in, and maybe the purpose of that machine was to do something else like multiply distance. Okay, so mechanical advantage greater than 1 means that the effort force was multiplied. And the mechanical advantage equals 1 means that the effort going in equaled the resistance coming out. And mechanical advantage less than 1 means that the effort decreased. And we are talking about absolute value here in the numbers. So we're not, when I say less than 1, we're not really considering the negative and the positives in these. We're just getting a ratio of the actual amounts and kind of neglecting the directions, even though technically we know that forces are always directed quantities, they're all vectors. But for right now, we're just considering the magnitudes. Okay, I still have everybody, right? Okay, cool. So this is almost like mechanical advantage, but it's our ideal, okay? When you have an ideal, that's the perfect scenario, right? If you're looking for that wonderful person that is ideal, you're looking for the perfect person. You're probably not going to find the perfect person. As a matter of fact, you know you're not. But you can find one that's pretty close, okay? Okay. And we want to think about that in our machines too. Okay, an ideal mechanical advantage, we can talk about it and we can think about it theoretically, but the actual ideal machine can't really exist because you can't get rid of all of the outside things that would keep it from being perfect, keep it from being ideal. There's no extra credit in mechanics, okay? The ideal is 100% efficiency. I know I haven't used that word yet, but the ideal is that none of the work that goes in is lost. Everything that goes in comes out. That will be the best you can do. You could multiply force so that the effort force is smaller than the resistance force, but you can never actually multiply the amount of work. Okay, the work in and the work out are two things that could, at the very best, ideally be equal, but you can never get more work out than work in. And that's an important thing I'll reiterate a lot as we go through. But let's think for a minute about this ideal situation where if we theoretically had the amount of work out equals the amount of work in. Okay? Output work equals input work. So none of your effort has been lost. There's no friction in such a machine, which you can imagine you can get it pretty low, but getting all the friction out just wouldn't be able to happen. So the work out equals the work in. So the work out is what we call the resistance force times what? What two quantities go into work? Force and distance. Good. So we have to have the work out is the force, resistance force times the resistance distance. The work in would be the effort force times the effort distance. I know you can see the little green marks starting to cancel some things out, but we need to get this idea of ideal mechanical advantage nailed down. So what we're going to do is we're going to make it so that we have FR over FE on one side of the equation because we know that that is our mechanical advantage equation. So what I want to do is I want to divide both sides by FE dr. I want to divide both sides by FE dr. I'm going to show you where the ideal mechanical advantage equation comes from. So, well, because if I divide both of these by FE dr, the drs will cancel over here, and the FEs will cancel over here. Remember, it's always math legal to divide both sides by the same thing. So we end up with FR over FE equals DE over DR. And a minute ago, we said what FR over FE represents. So what does FR over FE represent? The mechanical advantage. So in this case, when we have the ideal machine where all of the work out equals all of the work in, DE over DR is how we have that come out, and that is our formula for ideal mechanical advantage. Okay, there's two types of things we need to consider. We need to consider mechanical advantage, which is actually what really happened, and the ideal mechanical advantage, which would be what could happen if there was no friction and if the machine was ideal or perfect. So you have two equations right now. You've got your mechanical advantage, which is FR over FE, and we have our ideal mechanical advantage, which is DE over DR. In the problems that we're going to do, those numbers don't always come out to match. Remember, this is the theoretical one, if the work out equaled the work in. You right, Corey? How did I know to? Because I was trying to make it so that this is the mechanical advantage one. You're not going to be deriving this. in your future. But what I'm showing you is that mathematically, our mechanical advantage equals dE over dr. And mathematically, this does work. We have done the same thing to both sides of an equation, which you are allowed to do anytime. And we've gotten us to this point. I'm putting the I in front of mechanical advantage, substituting that in here though, because this only works when we've got an ideal machine. So we use the idea of efficiency. I talked about efficiency. I used the word because it's very hard to not use the word in the context of English. But efficiency is the percent of the work that comes out of the machine. I said the word's 100% efficient. But you can understand that in life, right? 100% efficient. So just if you're doing any kind of a task, Corey, and you're 100% efficient, what does that mean? You're going to get it done quicker, because is anything wasted if you're 100% efficient? No. So nothing is wasted if you're 100% efficient. In life, it's really impossible to be 100% efficient. Okay, 100% efficiency would be that idea of the ideal machine that I was talking about a minute ago, which it would be nice, and we can talk about it, and we can compare results to the ideal machine, which is what the efficiency percent does for us. But in real life, you're not going to get to 100% efficiency. We can do theoretical problems based on it, and it's good to try to get a machine, if you were designing one, to be closer and closer to being 100% efficient. But just like when you sit down to do your homework, you know when you've been more efficient or when you've been less efficient, because sometimes it takes forever because you're distracted by a million different things. I'm owning that for myself too. When I sit down to do something, there's distractions. So to be more efficient, I have to do good things like I can't have my cell phone turned up when I'm doing something, because just the little flashing when it comes, I can't do that. So if I want to listen to music, I actually literally have to turn it face down so I can't see the light. Some music distracts me. Some music does not distract me, just by whether it has words or not. So for me in life, more efficient is less distractions. For a machine, more efficient is less friction. And you can kind of relate that in. We do have some equations for efficiency. Okay, if you remember when you make something into a percent, you are dividing two numbers. This times 100 is just the way of telling you to move the decimal point 2 places over. I mean, quite honestly, it does belong here, but really we need to be in a place where you could just say, I need to find the percent efficiency, and just know that when you divide a part of a whole, if you wanted to make it a percent, you would move the decimal point over 2 places, and that's what's up with the times 100. So our output work divided by our input work. Remember, output work can never be greater than input work. So our percentage is always going to turn out to be 100% or less, even if we were talking ideally. So this is the easiest way to think about your efficiency or percent efficiency, how much of the work out compared to the work in. However, you might not have the information at the tip of your fingers for the work out and the work in. You might have information that leads you more to calculating mechanical advantage and ideal mechanical advantage, or maybe that's given to you. So the mechanical advantage compared to the ideal mechanical advantage also is a way of calculating this efficiency percent. So you can consider that. Now, mechanical advantage we said was what over what? FR over FE. An ideal mechanical advantage was DE over DR. So also in your book, they have this equation, FR over FE over DE over DR times 100. If you know this one, then you really can plug in very easily these, or you do the two numbers separately and then plug them in. That's fine. If we took this and we manipulated it a little bit, you would have work out over work in. So all these equations actually work together. And even if you had only one of them, you would be able to still do the math on it. But the way that the textbook is arranged, they chose to put it in 3 different ones. So I did that. All right. Good. So what that leads us to is it leads us to the type of things that could be measured for efficiency or measured for mechanical advantage, and that is the machines. We're going to deal with compound machines, but we're also going to deal with 6 simple machines. Okay, we have 6 different types of things that will allow you to either increase force or increase distance. And then as designers would take it, they would be trying to make them as efficient as possible. Okay, so we have a lever, and we will talk about these more in depth. We have a wedge. We have a pulley. We have an inclined plane, a wheel and axle, and a screw. And those are our 6 simple machines. So you will need to know what the 6 simple machines are. And what we're going to go over is how the effort and the resistance are arranged when you're looking at each of those 6 simple machines. The one that's got several variations is a lever. I'm only putting in the one type of lever on this, but I want to talk about the others. So I'll be bringing up a paint diagram and kind of running through some of the other ones as well. But our basic lever can be nothing more than like a rod or a plank or something with a pivot point, and that pivot point is called a fulcrum. And so whatever it is, the seesaw or whatever, will balance on this fulcrum, and you can put effort in, and that's going to push one direction. There will be an effort distance or displacement, so it will move the one side of the lever a certain length, and this would be our work in on this side, and the result or the resistance force would be what happened because of the effort coming in. So with a simple seesaw type of arrangement, it's easy to think you push down on one side and the other side comes up. If you are further away, notice my fulcrum is here. If you're further away, you can push to get a large distance and a small force. Great way if you were back in the day when they built log cabins or whatever, they need to lift something heavy, very nice and easy to make a quick fulcrum, push in. Crowbars work this way. So very many different ways to have this type of a lever. There are other types of lever as well, where the fulcrum is in a different place. I mentioned about like a baseball bat or a fishing pole, where it doesn't look like this. In that type of a lever, what you would have is you would have your fulcrum actually at the end. So you might have your fulcrum down here. Okay, this would be your fulcrum. And you could have your effort coming here. And then you'd have your result or your resistance would be out here. Actually, that should be smaller. because you're sacrificing force for distance. So you'd have your result out here. So you'd have your fulcrum here, you'd have your effort force here, and then your result here. So that's another type. And then the third type of lever, okay, would be if you had possibly like a wheelbarrow. And once again, you've got your fulcrum. You've got your fulcrum at one end. This would be like where you'd have the wheel, maybe the wheel of your wheelbarrow. So you've got something. And then you pull up on the end. So this is where your effort would be. But then the load would be being lifted right here in the middle. So you'd have your resistance in here. And in this case, actually, you've got your effort, but it would multiply your force. You're sacrificing you're putting in a lot of distance and getting a little and more force is being left out of it. You can usually lift things heavier with a wheelbarrow. With the baseball bat or the fishing pole, you're doing this, and then with our seesaw, you're doing this, and depending on how close you are to the fulcrum is going to determine whether or not you're going to be magnifying force or whether you're going to be magnifying distance. So lots of things going on with a lever. This is the one, though, that I want in your notes, in your picture. When you draw it on your test and you sketch it, I'll be looking for your resistance force, your yes. So something like that, where you're identifying where the effort is, where the resistance is, where the effort distance is, where the effort, where the resistance distance is as well, and where the fulcrum is. So a lever's purpose could be to multiply force. It could be to multiply distance, depending on what you're using your lever for. A pulley, so jot this down. A pulley, on the other hand, is most of the time, if it's a simple, regular pulley that doesn't move, in other words, it's fixed to a certain place, a fixed pulley, its purpose is going to be to change the direction of force. Okay. There are other pulley systems where the pulley is actually movable, where the pulley will go up and down, where you could multiply force. But in this case, for the most part, our effort and our resistance are the same, and the distances are the same. You're pulling down and it's up. So once again, not 100% efficient. You probably have to pull a little harder, put a little more effort in than what you're able to pull up. But the main purpose of a fixed pulley that's just attached to something is that it will change the direction of force, and then that can be useful. It can be useful even if it's not just an up and down. If you have a pulley, or you have a thing that's fixed and you're just running it around it so that you're changing the direction, it just helps, because maybe you can get a better vantage point where you're able to put in more force depending on what direction. You would put your, yeah, that's fine. Yep. Then we have an inclined plane. I don't have them in the same order as I put them down, because an inclined plane and a wedge are very similar to each other, but we have to talk about an inclined plane first. An inclined plane, another word for an inclined plane, is just a ramp. So you've got something that you're pushing up a ramp. You encounter them every day with wheelchair ramps. And you might think, well, I don't really have to think about wheelchair ramps, but you never know when somebody is going to have an accident and maybe temporarily need a wheelchair ramp, or maybe somebody has a family member that gets in a state where they're in a wheelchair for a little while. The school that I used to teach at, we had to come up with something and figure out a wheelchair ramp because somebody had gotten injured. And we see, you see people get injured all the time. So this idea of inclined plane, because it doesn't move, it's hard to sometimes think of it as a machine, but it actually is. And what it does is it allows you to take your force and spread it out over a longer distance as you're pushing whatever it is up the hill. And then it is much easier. And the result, this is an R, the resultant force is that it will pull it up that that distance from here to here without having to just take the whole thing, the wheelchair or the box or whatever, and just deadlift it straight up. So you're pushing here, and most people can help people when a ramp or an inclined plane is in use. So you have an effort that is not as great as if you would have to pull straight on up. Okay. You don't have to put the distances in, just the effort and the resistance force. So the effort force is going right along parallel, and then the resistance is the straight up. Now, if you take this inclined plane and you start to move it, we get what's called a wedge. So the wedge comes down and it starts to split out something. You see that with a hatchet. You see that with a doorstop that gets pushed in a door that will spread out, and it'll change the direction of force. It actually kind of splits it in two different directions. When you have a knife or a pair of scissors or anything that slices, what it does is it gets right in between the fibers. And so even though you're pushing down possibly with the knife, although the knife sometimes slicing actually helps, but the downward push changes the direction and pushes the things separately. Okay, a zipper kind of works on that same idea that it's coming down, it's pushing down, you're pushing this way, and whatever it is splitting out sideways. And it is, so the inclined plane is coming to the thing that's trying to be split rather than the thing going into the inclined plane. So a wedge. Although there are log splitters where we still call it a wedge, and the log is being pushed into the wedge. So movable is a relative term. We talked about that it depends on your frame of reference. Another one is a screw. Okay. And I do have some things I can show you hands-on after we finish, probably when we do next week's activities. I'll show you some things hands-on so you can be able to see these. Most of the time we think of a screw as the little device that goes into a wall. It takes a little force to turn the handle. So this here is the effort. So the effort is going in where the screwdriver is actually pushing kind of at a tangent. This is meant to be at a tangent, kind of hard to draw. As it goes around in a circle. So you've got the effort, and the resistance is this way. And the amount of force that pulls it together when you've got this screw is much greater. And when you put a screw into something, it'll hold it nice and tight. However, you can also use a screw in the context of, if you have it arranged right, you can be pushing something along. If you have the right kind of screw, we'll be taking a look at a C-clamp in class and getting some hands-on, and you'll see how a screw can be used for really pushing something along, which is very good. This one actually also is related to an inclined plane because it's like a spiral. So it is actually like a spiral-shaped inclined plane as well. And then the last one, our wheel and axle, is you're almost thinking about that as being the same thing as a pulley, but it's not, because in a wheel and axle, you've got a smaller axle and you've got a large wheel. And you're putting in your effort on the outside circle and it's affecting the inside circle. So you've got a long distance to go around this way. But when that translates to the small distance for the smaller circle, it will multiply your force. So you've got the effort possibly going this way. Notice that when you turn this around, it's going to spin this way. So it'll be pulling up whatever's on this side. But a wheel and axle can be used in many different contexts, like in a pencil sharpener, you could have a handle. When we go out, and I told you I was going to give you a little bit of how to change a tire, even though some of you have already done it. The jack that I have in my car has a wheel and axle where you actually turn the jack and use some various different things, and we'll identify when we take a look at the jack what those different pieces are. So you've got a wheel and axle, screw, inclined plane, all those different types. And then if you put them together in sequence, what you have is a compound machine, which is a combination of simple machines where the resistance from one becomes the effort of the next. And it moves on and on and on and on. So we will be doing that. Next week, we'll also be working on doing some calculations of mechanical advantage and ideal mechanical advantage. You should continue to work on your assignments. Make sure that you're working on the study guide, keeping those things up to date. And so next week, we'll be taking a look at a compound machine. And then eventually you're going to actually be designing your own compound machine. We're going to be doing a Rube Goldberg project. And that would be it.